Welcome to the second lecture on the design of steel composite column subjected to compression and uniaxial bending. Here in this lecture I am going to explain the resistance calculation of a composite column under combined effect. Here in the case of a column subjected to compression and uniaxial bending, the capacity has to be checked in two respective ways. The axial capacity separately and moment capacity separately, where PP is nothing but the plastic resistance of composite column for multiplied by a reduction factor to get the design capacity of column under compression load. To check the moment capacity, this is the plastic resistance of the column, which is multiplied by a reduction factor and 0.9, that is 90% of the strength to be taken as your design capacity, that is checked with the applied moment. This is the check you have to make to design any composite column under combined effect. So in the composite column, you have to check the second order effect. If the column having a ratio of P, that is the load acting on the column to the critical buckling load, if this ratio is greater than 0.1, then if the slenderness ratio of the column exceeds 0.2, then you have to consider the second order effect. The second order effect is nothing but you have to consider a modification factor for K is equal to 1 by 1 minus P by PCR. So if this ratio is to be calculated, this must be always greater than 1, and this factor to be multiplied by your moment acting on the column to take a correction on your effect of the column. That means your column having a moment that should be modified or increased by a factor due to second order effect. This is for to consider second order effect. If this ratio is not get satisfied, you can take only your effect. There is no need to consider the modification factor. Coming to the moment resistance check, that is the resistance of the column is nothing but 0.9 times mu into MPL RD, where MPL RD is nothing but plastic resistance of the column. To calculate mu, you have to follow this particular figure. I already explained this is nothing but the interaction curve of a composite column subject to uniaxial bending. Under ideal condition only, the column under compression will follow this line. Basically, the column member have some imperfection, say in the form of initial bow or residual stresses, or due to both the effect, the column capacity is reduced by chi times. Therefore, now the axial compression line comes in this way. So this is the axial compression line, and this is your moment line. Now here up to the chi c, there is no moment in your case, but when I exceed chi c, there is a reduction in the moment curve, that is this region. Since your ideal, it's not your ideal column, in your practical column have a reduction of chi factor. Now the mu is nothing but what is the moment reduction factor due to the imperfection in the column under compression. That is, if I am taking any point here, that is chi d, where my moment value, this is your compression value, this is your compression value, your moment value this much. So that is calculated by a value called mu. So therefore, the mu is calculated by this expression using the chi. This is your reduction factor of column. This is your chi d, which is nothing but your axial load on the column divided by plastic resistance. Chi c is nothing but compression capacity of the concrete by the plastic resistance. By this you can get the value of mu. This expression holds good only when your chi d is greater than or equal to chi c. That means when your chi d is greater than chi c, then your new expression will be the first expression. If your chi d is less than chi c, that is, if your chi d is less than chi c, then your new expression will be expressed by this expression. So using this, you can calculate what is the moment reduction factor. So moment resistance factor mu. So with this mu, you can calculate what is the resistance of your column under uniaxial bending. If a column is subjected to biaxial bending, then in addition to the moment check on one direction, you have to do it both the direction, both major axis bending plane as well as bind axis bending plane. This expression is derived based upon this equation. MD, that is your moment on the column, divided by mu times plastic resistance should be less than or equal to 0.9. So this is the way it is to be taken on the other plane also. But since you have a moment on either plane, then you have to check the combined effect of the two moment equation also. This is the interaction equation by this biaxial bending, where the linear expression is terminated at 0.9 mu x, that is axial compression with the moment is terminated here. But for your combined action of two moments, it should be taken to the full value of mu x and mu y. Therefore, your expression should be calculated like this. So this is nothing but about the major direction, the ratio between the applied moment to the resisting moment. About bind axis, applied moment to resisting moment, the sum of the moment should be less than 1. All the three equation has to be satisfied when a member is subjected to biaxial bending. So here, this is your mu x and mu y. Same expression, everything is same except in the chi, where in the chi you have to substitute the corresponding axis. Rest of them are same. So if you are able to remember this equation, just you put chi x, here chi x, you will get mu x. For this other condition also, chi d is less than chi c also. So with this information, you can able to calculate mu x and mu y. Thereby, you can able to satisfy the three equations. In the next video, I'll explain the step-by-step procedure of the design of composite column under uniaxial and biaxial bending. Thank you.